Chapter 5, you learn how to draw electron dot formulas for atoms. By placing the number of dots around each atom, the number of dots represent the number of valence electrons the atom has. In this chapter, you learn how to draw electron dot formula for molecules. It's also called Lewis structure. Molecule made up of atoms. So a Lewis structure shows the bond between the atoms, and it helps us visualize the arrangement of atoms in a molecule. There are 4 steps of drawing Lewis dot structure of molecules. Step number 1, you calculate the total number of valence electrons by adding on the valence electron for each atom in the molecules. Step number 2, you divide the total valence electron by 2 to find the number of electron pairs in the molecules. Step number 3, you surround the central atom with 4 electron pairs. The central atom usually is the atom of the element with the least number of the atom. When I go over the symbol, you can see, understand it better. Step number 4, if there are not enough electron pairs to provide an octet for each atom, that means 8 electrons for each atom, you're going to move the non-bonding electron pairs between the 2 atoms that only share an electron pair. They can have more than one shared electron pairs. So let's take an example. Writing the electron dot formula for water H2O. So between oxygen and hydrogen, oxygen had the least number of atoms, so it would be my central atom. So count the step 1, it count the total number of valence electrons. Oxygen has 6 valence electrons, hydrogen has 1. That 2 of hydrogen, that make a total 2 plus 6 from oxygen, that is 8 electrons. You divide by 8 electrons by 2, that give you 4 pairs total. So we're going to place the 8 electrons of 4 pairs around the central oxygen atom. So here's my central atom. I place 4 pairs of electron pairs, and then after that you place the 2 hydrogen atoms in any of the 4 electron pair position. I can put hydrogen here, I can put hydrogen here, I can put hydrogen here, I can put hydrogen here. Maximum of 2 hydrogen, because the chemical formula said only 2 hydrogen. Let's say I put on the right to make it look pretty. Now this is the Lewis dot structure of water molecules, and you see between oxygen and this hydrogen, the one electron pair. Between this oxygen and this hydrogen, there another electron pair. The electron pair, we call it bonding electron pairs. And the one on the top and the one on the bottom, it's not bonding with hydrogen, we call it non-bonding electron pairs. For water molecule, oxygen has 2 non-bonding electron pairs. Okay, now sometimes simplified, we can represent a bonding electron pair by using a single dash line. We call it single bond. And the resulting structure is referred to as the structural formula of the molecules. So I'm replacing is an electron pair here between oxygen and hydrogen by a single dash to simplify. For simplification, and each of this dash represent a single bond. And we call this a structural formula of water, or chemical structure of water. So H2O is chemical formula. This is chemical structure of water. Let's take another example. Write an electron dot formula for sulfur dioxide. Sulfur would make my central atom because it's an element with the least number of atoms. Now, then the first step, you count number of valence electrons. So each oxygen has 6. Sulfur also has 6 valence electrons. We make a total of 24. And then if you divide the 24 electron by 2, that gives you 12 electron pairs. Then the next step is to place 4 electron pair around the central sulfur atom, and then you attach the 3 oxygen atom around the sulfur. So we start with sulfur, place 4 electron pairs around sulfur, and then we will fill in the remaining electron pair around oxygen. You start with 4, you have a total of 12. That means that you have 8 left. So I'll put here 1, 2, 3, 4, 5, 6, 7, 8. After I fill in the electron pairs around oxygen, I realize the last one only has 6 electrons and not 8. Then step number 4, if you remember, tell you to move the non-bonded electron pair to where that atom needs to have electrons so that its octet is complete. So I'm going to move the electron pair to this oxygen because it needs 2 more electrons to complete the octet. Now when I move down here, you can see the 4 electron pairs shared between sulfur and oxygen. That means this oxygen had the 4 electrons. The sulfur also had the 4 electrons. Because of that, you count the number of electron pairs around this oxygen. You will see a total of 4 or 8 electrons. 1, 2, 3, 4 pairs, 8 electrons. For sulfur, 1, 2, 3, 4. That also 8 electrons. Therefore, the octet is complete. So I move this lone pair here, but there are many ways for you to move that lone pair electrons so to make the octet complete for other atoms. So I can move the electron pair here to share. So that will make 2 share electron pair. If I move this to here, like this structure here, would make this oxygen here have 2 electron pair sharing with sulfur. So the 2 share electron pairs constitute a double bond. So here is a single bond, but this a double bond. The double bond can be placed between the sulfur and any of the 3 oxygen. You can see they can be placed between the oxygen to the right. They can be placed oxygen to the left. It can be placed to the oxygen at the bottom one. The structure formula can be shown at any of the 3 structures I show you here. This phenomenon is called resonance. Let's take another example, electron dot formula of ammonium ions. We talk about molecule. Here's an ion because carry a charge, +1. The total number of valence electrons in this ammonium ion is 8 because nitrogen have 5, hydrogen have 1, but the 4 of them make it 4, -1 because of the plus charge, it means it lose 1 electrons. So now we have 4 pairs of electrons. Nitrogen would be my central atom. I put a 4 pair electron around it, and then for each pair electron, I put a hydrogen like you did with water. The difference is now you have to put a bracket to enclose the polyatomic ion, this polyatomic ion NH4, plus into a bracket and indicate the charge outside the bracket. So by the convention, you have to put a bracket for when you write a Lewis structure of an ion, and the charge you put outside of the bracket. So that ends up how this chapter, that's how you write Lewis dot structure of molecules. In the previous video, I'm talking about polar ionic bonds and covalent bonds. But in covalent bonds, there are 2 types, the polar and non-polar covalent bonds. Now, recall that covalent bonds are bonds that form by the electron share between the atom. So polar covalent bonds, they result from the sharing of valence electrons, right? That's the first thing. Now, often the 2 atoms do not share electrons equally. That means one of the atoms holds onto the electron more tightly than the other. And when these atoms hold the share electron more tightly, the bond is polarized. So a polar covalent bond is one with the electron are not shared equally between the atom. So how do you know one can hold stronger than the other? It depends on electronegativity. Each element has an innate ability to attract valence electron. That is electronegativity. It's the ability of an atom to attract electrons in a chemical bonds. And Linus Pauling scientists devised a method for measuring the electronegativity of each of the elements. And he concluded that fluorine is the most electronegativity element. So what would be the trend of electronegativity of element in the periodic table? The trend is it increases as you go from left to right, the electronegativity increase. And the electronegativity also increases from the bottom to the top in the family. So you see element on group 7, the far right, they has the highest electronegativity or higher electronegativity compared to element on the left of the periodic table. So you can calculate the electronegativity difference, and by doing that, you can predict if the bonds is polar or non-polar. Let's say the electronegativity of hydrogen is 2.1 and chlorine is 3. The difference between electronegativity of hydrogen and chlorine is 0.9, and therefore it's polar. There's a table in the textbook to tell you, depend on this number, the bond can be polar or non-polar. And we know that chlorine is more electronegativity because on the far right of the periodic table, so electron attracted toward chlorine more than hydrogen. And that gives the chlorine atom a slightly negative charge and the hydrogen atom a slightly positive charge. So you use an arrow to point to the atom is highly negatively charged, slightly negative charge. That's what by convention. Sometimes you can use the Greek delta, letter delta, to indicate a polar bond. So the negatively charged atom is indicated by the symbol delta minus, and the positively charged atom is indicated by the symbol delta plus. And it refers delta notation for polar bonds. So delta minus on chlorine and delta plus on hydrogen, because hydrogen is slightly positive and chlorine is slightly more negative, since it tend to point electrons from hydrogen toward. So delta notation for polar bonds apply to a lot of different molecules. Here show for hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. You see all of the elements on group 7, they have high electronegativity, so they all have the delta minus on it, whereas hydrogen have delta plus. For non-polar covalent bonds, what if the two atoms in the covalent bond, they have the same or similar electronegativity? So now the bonds between them is not polarized and it's a non-polar covalent bonds. If the electronegativity difference is less than 0.5, it is usually considered a non-polar bonds. Halogen molecule in group 7, remember, fluorine, chlorine, bromine, iodine, the diatomic, they are diatomic molecules. They are non-polar. They form non-polar covalent bonds. Here, the example of fluorine. So between these two fluorine, they have a non-polar covalent bonds. Between two chlorine atom is a non-polar covalent bonds, and so on. So hydrogen bonds is something that we didn't talk about, ionic bonds or covalent bonds. This hydrogen bond is special. It is the bond between hydrogen and oxygen and water, and it's very polar. Therefore, the oxygen is partially negative and the hydrogen is partially positive, right? Because remember, oxygen is on the far right side, so it has high electronegativity, so it's partially negative. And as a result, the hydrogen atom on one molecule is attracted to the oxygen atom on the other. And this intermolecular attraction is referred to as hydrogen bond, which you will learn in, later on. I will stop here, and I will stop here, and I continue recording this topic in the next video.